Ladies and gentlemen, good afternoon. It's a great honor for me to give this presentation. First, I will introduce myself. My name is Jinan Zhang. I worked at the first aircraft research and design and research institutes in China. During last 1 year, I worked with Wang Dongwang, Kevin Rans, and Renzin Benedictus in Delft University of Technology in the Netherlands for the crack growth in the fibre laminates. So today, my topic is an experimental investigation into the pin loading effects on fatigue crack growth in fibre laminates. There are 5 parts in my topic: the introduction, the text procedure, experimental result and analysis, discussion, and conclusion. So first of all, we can see from my topic there is an experimental investigation. So why do we need to do this test? Just as we know, the fibre laminates are a family of the hybrid structure which comprised with the metallic material and the composite material. And the glare, which one of the successfully developed fibre laminates, concluding the glass fibers, has been well known for his fatigue and damage tolerance behavior. So more and more glare has been used for the aircraft structure. For example, the A380 for the Airbus has been used the glare for the fuselage panel. We can see for the up fuselage panel here and here. Just we know the glare has been used for the structure in the aircraft fuselage panel, and we also know the load for the structure panel is mainly introduced by the ground-air-ground pressurization cycles, which creates a roughly constrained amplitude fatigue loading, and load is transferred from one panel to another when to the fastener in the fastener joint. So for this part, the fatigue and damage tolerance is an important part of the aircraft safety assessment. Moreover, we also know the Aloha accident which happened at the 1989. So if we want to address the MSD issue without understanding the effects of the pin loading effect for the fibre laminates, it is a necessary research and the requirement condition for analysis MSD for the fibre laminate joint. So that's why we should do this test. How do we do this test? We can see from the up picture, the symmetric double lap joints were designed to investigating the pin loading effect in order to eliminate the secondary binding. For the upper sheet was the specimen where the damage evolution could be observed with the cameras, and we use materials is glare 3, glare 3.2, and the aluminium sheet, the thickness of aluminium sheet is 0.4. And for the inner sheets, we use the material is glare 376, and the same thickness for the aluminium sheet. From these 2 pictures, we can see there are 2 kinds of tests we designed for this investigation. The only difference between these 2 tests is for this test there is only 1 pin pair, and for this type of test there are 2 pins for this specimen. And the pin is a titanium padlock fastener was used to join the specimens and the middle plate. For the test type 1, because its name is the single pin loading test, and the maximum load is 10 kN. And for the test type 2, we call it pin and bypass loading test. In addition to the load case of the specimen in test type 1, the ended fastener introduced the bypass loading to the crack in the specimen as a result of the load transfer in the type test 2. Okay, this is the test setup. The fatigue test was conducted on a computer controlled by on a 60 kilonewton fatigue machine. On one side, we can see we use the digital imaging correlation system to detect the delamination evolution at the interface between the outer aluminum layer and the fiber layer. On the other side, we use the high resolution camera to take the picture of another surface with the millimeter paper placed along the crack propagation direction. After test, the chemical agent was used to remove the outer of the aluminum layer to reveal the delamination shape at the metal and the fiber interface. That's the procedure of the test. So what we can get from this test? Previous study has found that the fatigue damage tolerance and the fatigue for the metal laminates can be divided for two main mechanisms. The first of all is the crack growth rate. So let's talk about this one first. We can see from this picture, the up two lines is the data from the pin and the bypass loading test. The below two lines is from only the pin loading test. For the crack growth for test 1 without bypass loading effect, the crack growth rate decreases as the crack length increase, and the crack stopped growing when the length reached at 10 mm. For the test type 2, the crack growth was affected by both by the pin loading and bypass loading. So we can see this line. The crack growth rate has the same tension trend till the crack length reaches the 10 km. Then the crack growth rate becomes stable onward. It can be easily found that the pin loading effect dominates the crack growth in vicinity of the pinhole. We can see here. And as the crack grows, the driving force from the pin loading for the crack growth becomes weaker. After the crack reached 10 km length for the test type 2, the bypass loading started dominating the crack growth. That's the result for crack growth rates. And secondly, the delamination shape. The left picture is an example of the stream measurements around the pin hand, often with the DIC system. The boundary of the red area we can see here and here is approximately the delamination frontier. And the red picture is a measure of specimen from the test type 1 after aging. So since the pin loading and the far field tension are not symmetric for the crack in the test specimen, so the non-symmetric delamination shape and the crack parts not perpendicular to the loading direction can be observed. We can say the delamination shape is not symmetric. It is like up direction. It is an angle for both sides of the hole. So we can see from this picture, it is the history of delamination extension, and the origin is here is the pin loading pinhole center, and for the red line is the agent management we can see. And for the black lines, it's a history of the delamination history. So the good correlation can be observed. The delamination shape matched with DIC system confirms that the delamination revolution and the propagation are not symmetric due to the non-symmetric pin loading case. That's the result. So what can we learn from this result? Just as we know, for the metal panel, the superposition method in the context of the linear elastic fracture mechanics is normally applied to calculate the stress intensity factor experienced at the crack tip. And after decomposition, the stress intensity factor for each loading can be easily derived. For example, this is a load case. We can decompose for this each of these load case, and we can calculate the stress intensity factor from each of these easily. So the question is this also available to use the superposition method for the fiber metal laminate joint? So we want to validate this hypothesis. We use the two data from the two type of tests. And we also use the Paris equation, and we transfer the equation like this. Due to the effect of the middle plate has a little bigger hair stiffness, we just talk about the material. The middle plate is the Glaire 376, so it's a total stiffness of the two out specimen, and the fact that's a small degree of the plastic deformation occurred during bearing. And so the fastener in type 2 joint transfer 10 kN respectively. Comparing the load of specimen in both joints, it can be easily found that the load for the crack in the specimen from type 2 joint can be decomposed into the load case for the specimen from type 1 joint and the bypass loading. And both the pin loading and the bypass loading are equal to 10 kN. So that's the result. We calculate the data of the test. This upper line is from the test type 2, and this two line is from the pin loading. And this line we use the Delamination model to calculate the stress intensity factor and the prescribed bypass loading. So we add this line with this line. We can shift this line here. The superposed result of the stress intensity factor range due to the bypass loading and the stress intensity factor range for the specimen in test type 1 carried well with the result of the test type 2. We can see this, the two types of line is calculated very well. So this correlation proves that the superposition method can be also applied for the fiber laminates. Finally, the conclusion. First, the effect of the pin loading accelerates the crack growth rate in vicinity of the pinhole, and the effect will be weaker as the crack length grows longer. Secondly, the load is not symmetric, so the crack opening should not be symmetric either, leading to a non-symmetric delamination shape. DIC test results and HN results validate this phenomenon. Stress intensity factor of pin and bypass loading specimen is superposed by the single pin loading and the equivalent far field load. The effect of the bypass load and the pin load can be calculated separately in the fiber metal laminate joint. Thank you for your attention.